Friends, today we are going to discuss the next type of reaction, addition of carbon-carbon double bond, or there is electrophilic addition to the carbon-carbon double bond, and that is the hydroboration oxidation. So hydroboration oxidation is nothing but addition of diborane B2H6 to the carbon-carbon double bond and to gives the alcohol. So it is the indirect method of hydration, because you know, when the water molecule is added to the carbon-carbon double bond in presence of concentrated H2SO4, then we get the alcohol. So this is the hydroboration oxidation. This is the method which is an indirect method for the preparation of alcohol. And what happened in this case, there is a syn addition of hydrogen and hydroxy group, and in this case there is a formation of 4-member transition state. So you take one simple example, and you take 3 moles of alkene. This alkene, they are treated with diborane in presence of tetrahydrofuran as a solvent, and then there is a first formation of trialkyl borane. This is a trialkyl borane, and when we call the hydroboration oxidation, so once you form the trialkyl borane, and this trialkyl borane is oxidized in presence of H2O2 and NaOH, then the bond between carbon and boron is cleaved, and then there is a formation of alcohol. This is 3 moles of alcohol. So this is a simple example of hydroboration oxidation. Means you take a alkene, 3 moles of alkene or 3 moles of alkene, then you take a diborane B2H6 in presence of tetrahydrofuran as a solvent, and first this BH3 is added to the carbon-carbon double bond, and then there is formation of trialkyl boranes, and after oxidation with H2O2 in NaOH, there is a formation of 3 moles of OH or alcohol. So what happened in this case? So we take a structure of BH3, and when we know the structure of BH3, then we remember this hydrogen is the negative part of the reagent and boron is the positive part of the reagent. So that's why what happened, which is a electrophile here. So the boron is electrophile because it having the electrophilic nature. So boron is added first to the carbon-carbon double bond to form the trialkyl borane, and then the oxidation takes place in presence of H2O2 in NaOH, and there is formation of alcohol. There is a cleavage of the bond between carbon and boron. So this addition is also according to the Markovnikov addition, because what happened when we think about this and we remember this is a olefinic double these olefinic carbons, and what happened according to the Markovnikov addition, the negative part of the reagents which is attached to the carbon which carries the less number of hydrogen atom. So which is a negative part of the reagent, that is the hydrogen. So hydrogen goes to here and boron goes to here. So this is a major product. So that's why we get here the less substituted alcohol. When you take example of hydration, what happened in hydration? Addition is according to the Markovnikov addition. But when we do the same reaction or hydration reactions with this alkene, then instead of the 1 propanol, we get 2 propanol as a product. But both the reaction is according to the Markovnikov addition. So that's why what is the importance of this reaction? We want to synthesize the less substituted alcohol, then we use hydroboration oxidation. We want the more substituted alcohol, then we use the simple hydration method, and then we synthesize that more substituted alcohol. So what is the mechanism of this reaction? So we see the mechanism. take here the simple alkene is there. Suppose you take this is alkene, then we add the diborane, this one. What happens? There is a formation of a transition state, and how the transition state is formed. In this way, there is a formation of a transition state. And you know this transition state having some cyclic character, because these two carbon, boron and hydrogen, there is a formation of a four-membered transition state. And we remember what happened. This reaction is very stereospecific or stereoselective. Here what happened? The addition of hydrogen and boron which are takes place in the same side. So this addition is a syn type of addition. Means hydrogen and boron or hydrogen and hydroxy group, they are coming from the same side of the these carbon-carbon double bond. So that's why once you do this, and then what happen? This cleavage of the bond between carbon and this boron takes place by oxidation, H2O2, NaOH, and then there is a formation of alcohol. We take this one, this is hydrogen, we write here OH and this hydrogen. So we remember this. Means this is the syn type of addition, means this hydrogen and this hydroxy group, they are coming from the same side. So this is a simple mechanism of hydroboration oxidation. The first, this boron is added to this, there is a formation of BH3 is added to the carbon-carbon double bond, there is a formation of a cyclic transition state which contain this four-member type of ring system, and then the after second step is oxidation, and then we get your alcohol. Both the hydroxy group as well as hydrogen both are coming from the same side. So that's why this is an example of syn type of addition. Then the next example, that is a hydrogenation. Hydrogenation. Hydrogenation is nothing but the addition of H2 in presence of catalyst to the alkene. We take one simple example. This is the alkene. We add the H2 in presence of platinum. This is called the catalytic hydrogenation. And hydrogenation is nothing but the addition of H2 in presence of catalyst, and then alkene is converted into the alkane. So this is a simple method for conversion of carbon-carbon double bond to the carbon-carbon single bond. Then addition of hydrogen is also the syn type of addition or cis type of addition, and the addition of hydrogen is always takes place in presence of the catalyst. Then we remember what happened. This reaction is an exothermic reaction. So hydrogenation is the exothermic reaction, because we know we break one pi bond and there is formation of a 2 sigma bond. So this reaction energetically is a favored reaction, and that's why in this case the one pi bond is break and 2 sigma bond is formed. So that's why heat is given out. So that's why hydrogenation is nothing but the exothermic reaction. And we know this reaction takes place in the catalyst. So what is the difference between the reaction which takes place in presence of catalyst and in absence of catalyst? So we know this is a potential energy, this is a progress of reaction, and when we take the simple example and then we see what happened. This is the alkene, there is formation of product alkane, and then we see these two type of reaction. So first reaction this is we know delta E, and this reaction is presence of catalyst, and this is the energy profile diagram for a reaction which is carried out in absence of catalyst, and this much amount of energy is required, and we call delta E2, this is delta E1. So we remember what happened when the reaction is carried out in presence of catalyst, or what is meant by the catalysis, or what is the role of catalyst. The catalyst is a substance which don't take part in a reaction, but it enhance or increase the rate of reaction. So that's why we take this is the two examples. So this first energy profile diagram, we carried out the reaction in presence of catalyst. So ultimately what happened, delta E1 is very less. Means when we use a catalyst, then catalyst decrease the excitation energy of that hydrogenation. When we do or we carried out the reaction in absence of the catalyst, so this much amount of energy is required to complete the reaction. So delta E2, so what happens when we don't use a catalyst, then this reaction having the more excitation energy, or it required more excitation energy, ultimately the rate of reaction is very small. So that is the importance of catalyst. In presence of catalyst, it increase the rate of reaction, but it don't take a part of reaction. So that's why this is hydrogenation is always takes place in presence of catalyst. Then what is the mechanism of this reaction? Means actually what happens when we use a catalyst. So we take, suppose this is your catalyst, and when we carried out the reaction in presence of catalyst, this is your hydrogen. So in first case what happen, this hydrogen is adsorbed on surface of catalyst. So that is the first step. When you take your alkene, then we bubble the hydrogen, H2 gas, there is a catalyst. So this hydrogen first adsorb on the surface of the catalyst. Then what happen in second step, the bond between these two hydrogen homolytically cleave on the surface of the catalyst, and what happen, the bond between these two hydrogen is break homolytically, and we say homolytically cleavage of the bond between these two hydrogen. Once the homolytically cleavage of this bond is break, and we form this type of compound in second step. In third step what happen, this is a hydrogen, means the bond between these two hydrogen is break homolytically, they are present in the surface of the catalyst, and also this what is your alkene is also adsorbed on the surface of the catalyst, and when alkene is adsorbed on the surface of the catalyst, here the pi bond or breaking of the pi bond. So this is the third step, means hydrogen is adsorbed on a catalyst, then bond between these two hydrogen is break by homolytically, then this alkene is adsorbed on the surface of the catalyst and breaking of the pi bond is there, and then in last case the transfer of hydrogen to the alkene. Suppose we take this type of your alkene is there, and both the hydrogen they are transferred from the same side to the alkene, and then in last case we get your product. This is your product, and here so we remove the catalyst, or catalyst is that is called as a dispersion of catalyst. So this is the mechanism of catalytic hydrogenation. Hydrogen is adsorbed on the surface of catalyst, then bond is break by homolytically, then this alkene is adsorbed by the surface of the catalyst and pi bond is break, then the hydrogen is transferred to the alkene from the same side, so that's why the hydrogenation is a cis type of addition, and then there is a formation of product, and finally the dispersion of the catalyst from your reaction mixture. So this is a simple mechanism, and these reactions we call as a catalytic hydrogenation. Then there is a next type of reaction, and this is called the ozonolysis. This is the next reaction we call the ozonolysis. Ozonolysis means the addition of O3. What happened in this case of addition of ozone? So ozonolysis is a degradation type of reaction. Means what happened? What type of alkene we use in a reactant, or alkene having the number of carbon in a reactant. In case of product, after ozonolysis, the number of carbon is decreases. So that's why this ozonolysis means the addition of O3 to alkene, and this is the degradation reaction. Then what happened in this case? What is the product we get after the ozonolysis? We get aldehydes, or we get 2 moles of aldehydes, or we get 2 molecules of ketone, or 1 molecules of aldehyde and 1 molecules of ketone. It totally depends on what type of structure of your alkene. Then first we know the structure of ozone, and this is the structure of ozone, O3. Then we able to write a resonating structure. We write like this, and when we write a resonating structure of ozone like that, and then we write a resonance hybrid structure. This is a resonance hybrid structure of O3, ozone, and actually this phases reacts with the carbon-carbon double bond. So what is the mechanism in this case, or how this O3 or this hybrid resonance hybrid structure of this is the O3, they are added to the carbon-carbon double bond, and there is formation of aldehydes and ketones. So first we see what is the mechanism, and in case of the mechanism, what happen when you take a carbon-carbon double bond and we take this is a O3 molecule, and what happen in case of the first step, this ozone is added to the carbon-carbon double bond, and there is a formation of molozonide. Once the formation of molozonide takes place in first step, then molozonide is converted into the ozonoid. So how the molozonide is converted into the ozonoid? So that's why this bond is break here. This oxygen get the negative charge, and this lone pair is given. So in this way, this molozonide is break like that. The bond between this carbon-carbon sigma bond is break to form the bond, double bond between carbon and oxygen. This oxygen-oxygen single bond is break. This oxygen get a negative charge, and this lone pair oxygen is given to here. We get a carbon-oxygen double bond. So once we form this type of compound, so we write this way, this way, and what is the next one? This is a carbonyl compound. Once the molozonide is break, this molozonide is converted into the ozonoid. This oxygen is attacked here, then this oxygen goes attack on this carbonyl carbon, and these electrons are given to the oxygens which having the positive charge, and then simply we form the molozonide. Ozonoid. This is a ozonoid. And once the ozonoid formation takes place, then in presence of water and zinc, this ozonoid is break, and then there is a formation of either aldehydes, either ketones, or aldehyde and ketones. It depends on, totally depends on the what is the structure or what is the substituents which are present on the alkene. So this is a simple mechanism of ozonoid, So ozonolysis is a degradation reaction because we know what is the starting compound. Starting compound having the, suppose the 6 carbon, but when we see the product, how many? 3 carbon. So this is a degradation type of reaction. And in case of this, ozone is first reacts with the carbon-carbon double bond. There is a formation of molozonide. Molozonide is break to form this type of two intermediates. These intermediates, they are reacts to each other to form the ozonide, and after ozonide is treated with zinc in water, and there is formation of aldehydes and ketones, or 2 moles of ketone, 2 moles of aldehyde, or 1 mole of aldehydes and 1 mole of ketone. So this is a simple example and simple mechanism of ozonolysis, and the product of ozonolysis reaction is totally depends on what is the substituents which are present on carbon-carbon double bond, or what is the nature of your alkene.